Deep learning models excel at finding patterns, but they immediately collide with a structural problem. The mathematical architecture of standard networks is completely rigid, while the physical, variable length reality is messy and dynamic. The foundation of this architecture is the baseline feed-forward neural network, or multi-layer perceptron. It is essentially a highly advanced calculator. This calculator operates under a strict geometric constraint. It requires its incoming data to be a fixed size vector, and it maps that data to a strictly fixed size output vector. To meet this requirement, raw data undergoes forced representation. Continuous numeric features, like temperature, are mathematically normalized onto a shared 0 to 1 scale. Discrete categories, like a word in a sentence, are transformed via one-hot encoding, placing a single 1 at a specific index to represent that choice. Once transformed, all these independent values are glued together, end to end, to form a single, flat, n-dimensional master vector. This forces a severe compromise. When faced with a variable-length audio recording or a complex spatial grid like an image, the network cannot dynamically grow or shrink its weight matrices to adapt. The raw data must be aggressively compressed, truncated, or flattened to fit the established input nodes. It is the mathematical equivalent of a coin sorting machine. The machine processes standard cylindrical tokens perfectly, but if you try to insert a paper bill of variable length, the slot cannot accept it. The bill must be shredded and compressed to fit the container. Forcing data into flat vectors destroys the inherent structure of time, space, and sequence. To process these dimensions accurately, we have to evolve the structural geometry of the neural network layer itself. Spatial data requires a property called translation invariance, the ability to recognize a pattern regardless of where it physically appears. Flattening a two-dimensional image into a single file, one-dimensional vector permanently severs native spatial relationships. The network loses the ability to recognize that a pixel on the left is physically adjacent to a pixel in the row below it. Tracing this, a 3-pixel image connects to a neuron with weights 0.8, 0.2, and 0.0. A far left pixel multiplies by the 0.8 weight, yielding a strong 0.8 activation. If that pixel shifts center, it multiplies against the 0.2 weight, and the output plummets. Because standard dense weights are permanently anchored to fixed coordinate slots, the network is entirely blind to the shift. It must relearn the exact same visual pattern from scratch every time it moves to a new location. Processing individual coordinates independently fails when the actual meaning is hidden in the local context and the relative position of the features. The first architectural leap to solve this is processing data sequentially. We break continuous data down into ordered sequences of fixed-size elements. Imagine a train station handling varying cargo shipments. A stationary crane cannot change its physical width to process a 4-car train all at once. Instead, the crane stays perfectly still, processing exactly one standard-size car at a time as the train slowly rolls forward. This logic drives the time delay neural network, or TDNN. A single shared set of network weights, a sliding kernel, moves across the data, applying the exact same mathematical extraction at every temporal position. It solves the shifting object problem by reusing the same parameters across the entire sequence. However, this sliding window is strictly limited. The receptive field equation, R equals m plus n plus 1, dictates the exact input geometry required. It defines a rigid boundary of how many past items, n, and future items, m, can be analyzed alongside the current target node at any one time. Constraining this context window restricts meaning. If an audio system isolates the word flight along with the preceding words, the birds took, the context implies biology. But if the window is wide enough to catch the future words, to Chicago was delayed, the true aviation meaning is revealed. TDNNs require ever-expanding, memory-heavy kernels to capture distant dependencies. To track an infinite sequence without expanding the window, the network must transition from static scanning to stateful memory. This introduces the simple recurrent neural network. An RNN builds a rolling representation. At any given time step, it computes its current hidden state by taking the new data from the current input and mathematically summing it with the hidden state it inherited from the exact previous step. To train this loop, the network undergoes unfolding
derivatives backward through every historical time step. RNNs successfully process variable length data by bridging time steps, but by chaining these mathematical operations together sequentially, they expose themselves to a fatal vulnerability over long distances. That vulnerability is the vanishing gradient problem. Consider a document where a crucial entity name appears at word number 5. The network must retain that exact specific context to correctly interpret a sentence 90 words later. A fractional weight like 0.9 multiplied 90 times decays to 0.000076. Information vanishes entirely. The solution is the constant error carousel. By forcing the recurrent weight to exactly 1.0, gradients flow backward indefinitely. A value multiplied by 1.0 90 times remains intact. Locking the weight to 1 creates an input conflict. A static weight cannot distinguish a critical entity to save from background noise to ignore. The network now requires dynamic logic to decide when to write, read, or erase. To resolve this conflict, we introduce a system that governs its own memory, the long short-term memory network. The LSTM uses dual pipelines, a top cell state for history and a bottom hidden state. A sigmoid forget gate erases outdated noise. An input gate scales new TAN candidate data, adding it upward. Finally, the output gate exposes the updated short-term hidden state. By managing an internal state, this architecture facilitates structure generation, a paradigm where the output layout is completely decoupled from the input format. In machine translation, the model takes an English phrase and executes an autoregressive sequence generation. It reads the context and begins outputting the German target phrase one token at a time. Ich wohne in Karlsruhe. At each step, the previously generated token is fed back in as the new input. The sequence length is dynamic because the model continuously evaluates the context until it mathematically decides to emit a structural end-of-sequence token, halting the loop. The LSTM is a self-regulating mathematical system that balances long-term storage, active execution, and dynamic structural generation without human intervention. Sequence models decouple the length of the data, but standard neural networks remain parallelized by their output layer. They still map predictions to fixed predefined classification boundaries. This creates a closed-set classifier failure. When a standard model encounters a completely novel, unseen class, it lacks the architecture to label it as unknown. It is mathematically forced to assign the input to one of its existing labels. If a voice identification model is trained exclusively on pre-registered profiles and an unregistered speaker talks into the microphone, the network will process the audio wave and erroneously label them as a known target, like Nagelsmann. Handling the unknown requires open-set metric learning, driven by Siamese networks. This framework uses twin subnetworks sharing exact parameters. Instead of mapping an input to a static class label, it maps two separate inputs into a continuous geometric embedding space. The network evaluates these embeddings using cosine similarity. By dividing the dot product of the vectors by the product of their lengths, it measures the exact directional angle between the data points, completely ignoring their magnitude. This spatial alignment is optimized using triplet loss between an anchor, a positive, and a negative sample. If the negative maps too close, high loss triggers an update, pulling the positive closer while pushing the negative away. Finally, applying a margin safety buffer ensures once the negative is pushed far enough outside, loss drops to 0. By optimizing for relative geometric distance rather than strict categorization, the network can process novel, unseen elements. It calculates how close a new vector is to established clusters, enabling it to map and flag the unknown. We began with a baseline architecture trapped by flat, static vectors. To process reality, we evolved the network to scan sliding sequences, manage stateful internal memory, and measure infinite metric spaces. Advanced deep learning relies on matching the mathematical topology of the network to the underlying geometric reality of the raw data. Multi-layer perceptrons map isolated features. LSTMs trace contextual timelines. Siamese networks calculate structural distance. By mastering data representation, dynamic gating, and relational metrics, neural networks completely transition from rigid calculators into fluid systems capable of decoding the complex architecture of reality.